Hello and welcome to a new video for Tackle Math. My name is Chris. In this video we're going to be using my new favourite website, which is Desmos, to try and recreate this pattern of a circle with a tangent to that circle which is rotating around the circle. So, first thing to do is to start with a new blank graph. So here we have a new blank graph, and to this blank graph we are going to add a circle, and the equation of a circle is x squared plus y squared equals r squared, where r is the radius of a circle. Now what Desmos does, if you haven't got if you've got a letter there that it doesn't recognise immediately as x or y, or some other things like pi and e, which it recognises straight away, is you're offered the chance to add a slider. Now a slider is a way of changing the value of that variable by moving a point along a line. Now it automatically defaults to minus 10 to 10, which the radius of the circle, I'd rather just keep it to being 1 and 6. So then there we go, that's our circle. We can go down to a radius of 1 and we can go up to a radius of 6. Okay, now if somebody knows Desmos better than me, you can explain to me why for some reason R doesn't allow me to do the animation feature. I don't know why. So I'm actually going to choose for my radius circle the value B. So that's partly all my note later on. I've chosen B. It's an arbitrary letter to represent the radius, which isn't R. So I'm going to add a slider for R, and then you'll see why I do that is I can then press that button there, and I'm on hands-free now. Well, actually, what I haven't done there is I haven't changed the radius back to 1 to 6, which I meant to do. Okay, so now it'll just be making that circle between radius of 1 and radius of 6. Gets bigger and smaller as that point moves along that line. Okay, so what I'm going to do now is I'm just going to get rid of that. I'll add that again in a moment. And I'm just going to set a radius of 4. Okay. So now I'm going to go back over to here. I'm going to try and start thinking about how we're going to write on there an equation of a tangent, which isn't quite as well known to me as the equation of a circle. So let's see if I can work that out. So we can work that out together. So if you've got a whiteboard open, you can see, to create my drawing. If you've got Desmos open, you can work along with me. So a point on the circle, we draw a little triangle. Again, I'm calling my angle in the middle G rather than theta, because theta's got special properties in Desmos. I'm just calling it G. B is my radius. X and Y are the coordinates of the point P, where P is a point on the circle. And you can see now we've got a right angle triangle. So we can actually work out the coordinates of P in this triangle. So first of all, let's write down the two trig functions for the circle, which are, I'm just going to minimize myself now, like that, so I've got a bit more room. Cos G equals X over B. That's just using the trigonometry in this triangle of the adjacent over the hypotenuse is the cosine of that angle. And similarly, we've also got sine G equals Y over B. And we can get values of X and Y at P by multiplying both sides by the B. So we get X equals B cos G and Y equals B sine G. So the equation of that point P is B times cos G, B times sine G. Okay. So now the equation of the radius, we now go, actually before we do any more on that, let's go back here and we're going to actually put in a point P equals B cos G. You'll see as you're doing things on Desmos that it sort of tries making a guess of what you're going to do. It's not really worth looking at too much until you actually type in what you actually want to do. There's a nice pretty sine curve there for a moment, cosine curve there for a moment. So we've now got B cos G, B sine G. G is a new variable which we don't know, so we add a slider. And because we're talking about an angle, we're going to be working radians. Let's have that go between 0 and 2 pi. If you just type pi, it corrects itself to the pi symbol we're familiar with. And then you press G going, then the point goes around the circle. And we can see all the points where it follows the rule B cos G, B sine G are points on the circle. And it moves around the circle as G changes. So let's just stop that. Go back to my whiteboard. Now we're now going to just draw a radius on. Now the equation of the radius is in the form y equals mx plus c, because that's the form of any straight line. But because we know the radius is going to the centre of the circle, and because we've made the centre of the circle the origin, that means we don't really need to see. That's the y-intercept. We know that it's intercepting at y equals 0, so we can leave the c off. So the equation of the radius is y equals mx, where m is the gradient, and the gradient of this line is the y value over the x value, which is y over x, which equals tan g. Just put the multiply in there just to be consistent there. So the equation of the radius is tan g, or well, m is tan g, so the equation of the radius is y equals tan g times x. So we come back to here, put a new line in, y equals tan g x, and then you see the line is going all the way through because we haven't limited it to just being inside the circle. We can do that actually with a range. So if I say 0 is less than or equal to, if you do less than or equal to, you'll see it's one after the other. You'll see it actually replaces it with that sign, the combined sign for less than or equal to x. That's going to happen again. And then the value of x, which is b cos g. And now you'll see we've just got the radius inside the circle. We're not got it exactly right because it's only working. It's not working on that side because I've limited to being greater than 0. But I'm only really interested actually in the first quadrant at the moment. We're not leaving that line now. That if remember the construction we were trying to create didn't have the radius on it. I'm just including it there so we can use that to think about what the equation of the tangent is. And of course, the equation of the tangent works on the basis that the tangent is at right angles, is a perpendicular to the radius. So back to here, and we've got the gradient of that tangent is minus the cotangent of g. That's the gradient. Because that's following the rule that if you want lines to be perpendicular, it's going to follow the rule minus 1 over the gradient of the line we're trying to be perpendicular to. So what I've done there is I've taken the minus and I've put 1 over the tangent, and we get the cotangent. So that is the gradient of any tangent where we know that g is the angle made in the middle. That g is changing, as you saw the first bit. That's how we're going to get the thing going around the circle. So that means the equation of the line of the tangent is going to be the form C take away the cotangent of G. Now, that's just another way of writing y equals mx plus c. I've replaced the, we've just left the x off. Let's have the x on as well. The cotangent is the gradient. So the cotangent of G, or minus the cotangent of G, is the gradient of this line. C, we need this time because the tangent doesn't go through the middle. So there is going to be another constant in there, which is the y-intercept, which we're now going to try and work out what that is. And then minus cotangent. I write it that way around because I tend to put minuses after other things if I can. Okay, just my way of writing things. So we're now going to try and work out what C is, and we're going to add the cotangent gx to both sides. So we get C equals y cotangent of gx. And now we're going to use that equation with the values of x and y we know are on the circle, because that's also going to be the point that also exists on the tangent. So we can put the values of x and y at P into that equation and get B sine G, which is the value of y at P, plus the cotangent, right, I say cotangent, I'm actually writing it now as, let's just move that up. Otherwise we can't see what we're doing. I've written the cotangent now as cos over sine, and there's a reason for doing it that way. It makes it a bit more easier to simplify in just a moment. The cotangent is the same as cosine over sine because the tangent is the same as sine over cosine. That's how these ratios are actually related to each other. Times b multiplied by the cosine of g. B is cosine of g, which is the value of x at p. So all we've done there is we've taken the value of y and the value of x, and we replaced the cotangent of g with cos over sine. Because now we're going to simplify that. I'm factorising because I've got b in both of these two. So I've taken the b outside of the brackets. Inside the brackets, we've got sine squared g. Again, I'm going to have to move things up a bit. That is sine squared g over sine g. That's the same as sine g. I'm just putting the fractions over the same denominator. So I have to change this into sine squared g over sine g. So it all becomes one great big bracket. Plus cosine squared of g. If you're not familiar with this format, with the trig functions, we tend to put the squared between the function name and the brackets, just mathematical notation. So now what we've got there at the top now, you may recognize sine squared g plus cosine squared g. That's one of the first trig rules that you learn once you just stop using the trig for GCSE, and when you're actually looking for patterns between the trig ratios. Sine squared g plus cos squared g is always equal to 1. It's one of the trig identities, the simplest of the trig identities. So we can actually replace that now with b cosec g. Now cosec g is a trig ratio. Not one of the first three you learn, but one of the next you learn is the same as 1 over sine g. Because I've replaced the top with 1, because that's what the trig identity for sine squared plus cosine squared is. And so we end up with B cosec G, and that is the value of C. So then we have the value of the equation of the tangent becomes y B cosec G, take away cot G x. That's just putting the value of C back into here. So I think that's where we have to go back here and type in an equation of a line, y equals, cosec is, in Desmos we just use 3-letter code, so we don't write cosec as in full, it's just CSC is the name of the function for cosec in this, in Desmos. So, and take away cotangent of G x. I've made a mistake there somewhere. Oh, that's because I've forgotten to stick the B on. It's B, because the B's on the front. B on the front of the cosec. Sorry, I left the B on. I knew I'd done something wrong there. Okay, so let's get rid of the radius there. We don't really want the radius. I left the B off the front there, which if I go back to my the B there, I left it off. I say I could see something was wrong. So now what we're going to do is we're going to press that so G goes round in circles. Now actually there we've got it goes round, and then when it gets to a point it starts going the other way. We actually change the way that the slider works by clicking that, and that means it always goes forwards. And that means we've got our tangent going round the circle. Actually, if we were to change the that from a minus to a plus, we actually have that going the other way around the circle, but we're not now following the point P. We can turn that off. So actually, if we'd done the working out slightly differently, so the point was going the other way around the circle, we could have had the line going clockwise, but actually the problem I set was going the other way. That's what we've been working on. So put a minus in there. The tangent goes around the circle in the anti-clockwise direction, which is what we were looking for. Now there are various other things I could do with this. I could make the circle get smaller and bigger at the same time, just by doing B. And see, because of all the work out we've done, because B is part of the equation, the tangent stays on the circle as it gets bigger and smaller. While I was doing the working out, I was just sticking a B equals 4, but we don't have to. So that's a slight advance. The other thing we could do, which I've not done in this video, and would actually make the algebra a little bit more complicated, is we could change the center of the circle. So the center of the circle was not always the origin. Now that's something for you to look at if you want to take this a little bit further, but I'm not doing that in this video. Okay, so this is the first of several videos I'm going to make about Desmos, maybe about the GCSE syllabus, but Desmos is a really useful tool. So what I'm going to do is to end with a little sales pitch. Go to Desmos, open yourself an account. There are some other videos on YouTube, not made by me, but made by Desmos and other people who know how to use Desmos, showing all the things that Desmos can do. But it's a very useful tool for to look at the relationship between geometry and algebra, the way that things on the Cartesian plane, which is the way of the XY plane, can be represented through equations. Try doing some trigonometry functions, some polynomial functions, and just see how they look by using Desmos. If you're familiar with plotting graphs, you'll love playing with Desmos, I think. Okay, thank you very much for watching this video.